Good morning, ladies and gentlemen. I'm very pleased to be invited to be able to address you today on matters concerning general relativity and the non-existence of the black hole. It's also a subject, of course, that's fascinated many people, but it really doesn't have any real sound basis in any science, neither in general relativity or Newtonian theory. So before I get started on it, I'd just like to go over, make a few little comments about these black holes, because there's been some developments in recent times. Like, these black holes seem to be reproducing like rabbits. What we get is, let's go quickly through a whole list of things that we have with black holes. We start off with micro black holes, mini black holes, intermediate black holes, what we might call a regular black hole. Then we've got supermassive black holes. Now recently, they've been talking about ultra supermassive black holes. And I'm waiting with bated breath for the next one. Maybe it'll be a mega, ultra, super massive black hole. Well, the proponents of the black hole seem to just add adjectives and think that that makes it, gives it a more scientific validity. Well, adjectives don't do that. That's linguistics, it's not science. So I don't think that that's going to help them. The other thing is, of course, we're starting to get lots of reports of photographs on the internet and in journals and so forth and things. And you get things like, see that part you can't see? Yeah, it's a black hole. The other thing is, see all of those shiny things that shine brighter than stars? Those quasars? Yeah, well, they're black holes too. So we now get reports, for example, on quasar 3C279, which is reported as being a black hole. Well, as the previous speaker pointed out, Halton Arp has been speaking about quasar ejections. So what do we got now? Black holes ejecting, being ejected from what? Each black holes are supposed to be sucking up things, digesting matter and gobbling up the universe. Of course, then we have white holes. They do the opposite. Instead of gobbling up black holes, they vomit matter back into the universe. So, and then we've got wormholes, another whole thing. Whatever they are. Anyway, so we see that there's some very dubious ideas here. And what I'd like to do is to give you a number of proofs that black holes are not predicted by general relativity at all. That's the first thing. They're not produced by Newton's theory, contrary to what is claimed by proponents of the black hole, because it doesn't have the signatures of a black hole, and I'll see that, and I'll show you that. And so there are other proofs that I could give, but I've tried to limit myself to those proofs that don't require much in the way of mathematics, because I don't want to bamboozle anybody with the hocus pocus of tensor analysis and differential geometry that Einstein and his followers have been hiding behind for nearly 100 years, confuse everybody, and then say, we can't talk to you people, you don't know how to do sums. So what we'll do is now we'll move on to perhaps the first proof. Now, I'll read it to you, of course. Einstein's field equations couple the gravitational field contained in the curvature of space-time with its sources. I've given there a citation there from a source of this comment. And we can reduce this to some simple words, where we have space-time geometry equals minus kappa times causative matter, that is sources. Well, kappa is nothing other than a coupling constant, so that's no big deal. Space-time geometry and causative matter. Well, we go to the next line and we see this is the mathematical form of it. This is a tensor equation. There's nothing frightening about this. People go into an apoplectic fit when they see a tensor equation and think, oh, I'm out of my depth. Well, that's not true. When we break this down, you'll see that you will not need to know anything about tensor analysis, have no need to be able to make a calculation in tensor analysis, and not really know much about or anything about differential geometry to be able to follow the arguments that I'm now going to present to you. So the words space-time geometry equals kappa times causative matter are reduced to this simple expression where G sub uv is called the Einstein tensor, and it describes space-time geometry, the curvature of space-time, which Einstein says is the gravitational field. Now we see that this is a relationship between the curvature and the causative matter. So space-time and its curvature, the so-called gravitational field, is coupled to its sources. So there is a causal link between space-time and material causes. These subscripts here take on the values of 0, 1, 2, 3. They add a little bit of complication to it, but they're not frightening. Now, there's some simple terminology that I would like to use because you'll come across this as we go along, is that if we have a tensor T with subscripts, it's just called a covariant tensor. If it's a tensor with superscripts, it's called a covariant tensor. And if it's a tensor with superscripts and subscripts, it's called a mixed tensor. There's nothing difficult about that. The final thing that we have is the order of a tensor is equal to the number of suffixes. Well, when we look at the equations up here, we see that Einstein's field equations are second-order tensors because they're two subscripts, u and v. That's it. Okay. Now, we come to Einstein's so-called field equations from which the black hole is derived. And Einstein says that if T sub uv equals 0, his G sub uv reduces to R sub uv for empty space outside a body. And R sub uv is called the Ricci tensor. So I've written it as Ric, which is not that often used, but is sometimes used in the literature. So Ric equals 0 is supposedly a set of field equations that describe the gravitational field outside a body. Well, so we ask now, what then is the source of the gravitational field outside a body? Bearing in mind that he's already removed all the sources by setting the energy momentum tensor to naught. So he's taken out all the matter that causes the gravitational field with one hand, and then he uses the words outside a body to re-put in, or to put back in, the very notion that there's a source present. So this is a bit of linguistic mumbo-jumbo. What you've got now is no matter, but an object present. It's a contradiction. In fact, if we ask Einstein, what's the relation to Hilbert's solution for Ric equals 0, he says M denotes the source, or M denotes the sun's mass centrally, symmetrically placed about the origin of coordinates. So the introduction of mass here is done by some sort of surreptitious linguistic method. We've taken it out and put it in with another idea. It's a circular argument. And so this idea that Ric equals 0 actually is quite meaningless. Now, as I said here, it's a subtle play on the words outside a body. Well, so it's meaningless. It contains no matter, because that's what the meaning of the energy momentum tensor is. That's the matter part. Well, if it's gone, you've got no matter. So what have we got here? A set of equations that describes a totally empty universe. Well, that doesn't describe anything. You look into the sky and what do you see? It's not empty. Now, there's one other point I'd like to make, as you see on the bottom here, is that the black hole was obtained from a Hilbert solution. David Hilbert was a German mathematician, and he was working contemporaneously with Einstein, and he came up with the field equations, same as Einstein, evidently shortly before Einstein, but that is not commonly known. But it is not Schwarzschild solution, even though it goes by Schwarzschild solution, the so-called solution to this set of field equations. All you have to do is look up Schwarzschild's original paper, which I've done, and you find that the solutions are very different. Schwarzschild's solution doesn't allow a black hole. Hilbert's solution, which was a corruption of Schwarzschild's solution, is misinterpreted and allows a black hole, supposedly. We'll see how why. Okay, so we see from the first proof that we've got a circular argument where there's allegedly matter, but then there's actually no matter. So this doesn't describe anything. So in other words, when you set the energy momentum tensor to 0, Einstein's tensor can't reduce to Ric equals 0. So the whole idea of that is fallacious. And the solution to that, of course, means it's fallacious as well. And that's Hilbert's solution, Schwarzschild's solution, and any other solutions. They're all the equivalent solutions to these. That's a pretty simple proof that the whole idea is very dubious. Now, if we come to the second proof, Einstein asserted that his principle of equivalence and his laws of special relativity must hold in sufficiently small, finite regions of his gravitational field, and that these regions can be located anywhere in his gravitational field. Now, I'll point out that both the principle of equivalence and the laws of special relativity are actually defined in terms of the a priori presence of multiple, arbitrarily large, finite masses and photons. Right? And we see here a quote from the Dictionary of Geophysics, Astrophysics and Astronomy. Black holes were first discovered as purely mathematical solutions of Einstein's field equations. This solution, the Schwarzschild black hole, is a nonlinear solution of the Einstein equations of general relativity. it contains no matter. Yeah, well, we already established that. And exists forever in an asymptotically flat space-time. So, since it's empty, it can't be a black hole. Now, there's another point here. This is a black hole, and all black hole solutions pertain to a universe that allegedly contains only one mass. So, the universe contains a lot more than one mass. And what you mean by a gravitational field to a universe that contains only one mass? First, it doesn't model anything realistically. And how do you detect the gravitational field if you don't put in some other masses? Well, we've only got a one-mass body here, a one-mass universe. So, you can't get a black hole. Doesn't make any sense. Now, the principle of superposition doesn't apply in general relativity because Einstein's field equations are highly nonlinear. Now, mathematically, this is a very simple expression. If you have a solution x and y, two separate solutions, then the linear combination, ax plus by, is not a solution. All right? That's what the principle of superposition means mathematically. Well, when we talk about it physically, this simply means that one cannot pile up matter into any given space-time solution to obtain additional matters, charges, photons, and electromagnetic fields, etc., as desired. So in other words, you've got a black hole solution. It contains one mass in the whole universe. You cannot then just arbitrarily say, oh, what I'll do is I think I'll put in another black hole and another black hole so that all these black holes mutually exist and mutually interact in a mutual space-time that by mathematical construction contains no matter. How does that work? Well, they do, the proponents of the black hole actually just do that by a false analogy with Newton's theory. Because in Newton's theory, there is no relationship between matter and space. There is no causal connection between them, and the principle of superposition applies. And that's why in Newton's theorem, or Newton's theory, we can have as many masses as you like. Now, if you want to work out the interaction of three bodies revolving around each body centre of gravity, it becomes very complicated. And beyond that, we can't solve them because the equations become too difficult. But there's no conceptual reason why you can't stick in all sorts of matter, photons, lots of stars, and the rest of it. But in Einstein's theory, you cannot. This means that every single configuration of matter that you propose for a solution to Einstein's field equations must be described by an appropriate energy momentum tensor, and the field equations solved separately for that particular configuration. That's never been done. Why? Because there are no known solutions to Einstein's field equations for two or more masses, and there's no existence theorem by which you can even assert that his field equations contain latent solutions for such configurations of matter. So all solutions to Einstein's field equations pertain to only one of two things: a universe that contains nothing, or a universe that contains one mass, whether it be cosmological or otherwise. That models nothing in reality, and it has really no meaning, because we know from experiments that gravitation is an interaction between two bodies. And this is, for example, in the experiments of Cavendish. You take two cylinders, or two spheres, spherical bodies, they're suspended, they're fixed, and then you release them. They'll approach one another. Okay? You take one, well, what else have you got? You know, there's nothing to do with it. It just sits there. Okay, so again we can say that Rick equals 0 is a space-time that by mathematical construction contains no matter, and owing to the principle of equivalence, you can't stick in more. So the black hole can't possibly exist because it's a one-body solution, right? I'll come to some other issues shortly and show you that that doesn't even make sense. So a few more comments on this proof 3. As I said, there are no known solutions to his field equations for two or more masses. No existence theorem by which it can be asserted that his field equations contain latent solutions for such configurations. So all talks of multiple black holes is quite meaningless. But what do we get told? Mr. Hawking tells us for existence, oh, black holes are merging. Black holes are in binary systems. Black holes collide. Where did he get all these extra black holes? He just stuck them in. You can't do that. It's impossible in Einstein's theory because it's a nonlinear system. Just like in nonlinear systems of differential equations, you can have solutions two different solutions to a linear differential equation, add them together, and that creates another solution. If you have two separate solutions to nonlinear differential equations, you add them together, you don't get a solution to that nonlinear equation. That's it. Okay, so as I've remarked before, I'll just reiterate that all black hole solutions pertain to a universe that allegedly contains only one mass, and so they are totally invalid models. Proof 4 is a little bit of mathematics here. Don't be frightened of it. It looks complicated, but when we break it down, it really becomes pretty simple. Now, this is Hilbert's solution, and usually they write C and G equal to unity. And so you get a simplified expression, but that hides everything. It's a bit slick, but so I've written it here with C and G explicitly, so nothing can be hidden. And you'll see why I've done that and how black hole escape velocities are allegedly obtained, how radii of so-called event horizons are obtained, and we'll see that that's really another fudge, because there are things called the components of the metric tensor. We can easily read them off. We don't have to really know greatly what we mean by a metric tensor, but first I'll say what we mean by a metric. Well, they're either called line elements or metrics. This is nothing other than a fancy name for a distance formula. And we all learned in high school how to calculate the distance between 2 points with coordinates x1, y1 and x2, y2 in the Euclidean plane. So you get delta s squared is equal to delta x squared plus delta y squared. You can extend that to 3 dimensions and add a delta z squared. It's a distance formula. And in that case, all the signs of the components are positive. Notice in this one, it's very, very strange because the time part, which has got the dt squared there, is positive, and all the other parts are negative. So we call it a pseudo-Riemannian metric space because it relates to Riemannian geometry, and because of its differences in signs, it's called pseudo-Riemannian. Just complicated names for some complicated mathematical ideas. So what we really want to know is components of the metric tensor for this expression. Well, we can read them off. It's really easy. And we'll give the names for the metric tensor G with two subscripts on them because we're dealing with second order tensors. So G naught naught is 1 minus 2 gm over c squared r, G11 minus 1 over 1 minus 2 gm over c squared r, G2 minus r squared, and G33 minus r squared sine squared theta. What you see is that these are nothing other than the coefficients of the differential elements that appear in the first expression. Okay, now, before I go on to do an analysis of these two G naught naughts and G11s, first we want to identify what R is. This becomes quite hilarious. Here's what the proponents of the black hole tell us. The quantity R has been variously and vaguely called a distance, the radius of a two-sphere, the coordinate radius, the radial coordinate, the Schwarzschild R coordinate, the radial space coordinate, the areal radius, the reduced circumference, the shortest distance a light ray travels to the centre, and finally, a gauge choice. It defines the coordinate R. Now, in the particular case of R equals 2gm over c squared, it is invariably called the Schwarzschild radius, or the gravitational radius, namely for the radius of the event horizon of the black hole. Well, there's a lot of definitions here. Which one do you want to pick? No? Well, they're all wrong. It's easy to prove. Then to reiterate a little bit further on this, in his paper on a stationary system with spherical symmetry consisting of many gravitating bodies, Einstein himself continually and incorrectly refers to R as a radius. You can easily verify that by looking at the paper. You can download it from the internet. So with all these definitions, what do you conclude? I conclude that there's utter confusion. That Einstein and his followers just don't know what R is. That's the truth of it. With all those definitions, as I said, it's just an arbitrary choice. But this is a geometric relation. And so we must have a definite geometric relation for all the components in this expression. Okay, so The correct identification of R completely invalidates the black hole once again. Well, you'll never see it in the literature because I think I'm the only one that ever made the calculation. So let's consider the identity of R just for the fun of this. Now, as we saw in the previous expression here for the metric, there was a time part and a spatial part. Well, I've taken out the spatial part. It's got all positive signs because you saw that it was the time part minus all the spatial bit. Well, so the spatial bit is just all of this. It's all positive signs. Now, if we take the surface in this spatial section, that's the last bit on the end here, r squared, d theta squared plus sine squared theta d phi squared. There are only two variables here. The things that are variable are theta and phi. They're angular quantities. R doesn't change. You know, it can change later when we're looking at the later metric, but we're going to consider this surface. Now, there is a thing called Gaussian curvature. Gaussian curvature is a property of a surface, and it's an intrinsic property of a surface. Carl Gauss proved this long ago, and that's why it's named after him. Now, it's independent of any embedding space. What do I mean? If you take this surface and you embed it in ordinary Euclidean 3 space, for example, right? That doesn't change the nature of the intrinsic geometry of the surface. So we can consider the intrinsic geometry of the surface without any consideration of any embedding space, whether it be Euclidean 3 space or the very complicated looking four-dimensional pseudo-Riemannian space-time metric that is proposed by Einstein and his followers. So, how do we calculate the Gaussian curvature of a surface? Well, it's really easy. Any differential geometry book will tell you if the Gaussian curvature is K, it's equal to R sub 1212 over G. Well, when we look at R sub 1212, well, we recognise that as a tensor. What order is it? Well, we count them up. There's 1, 2, 3, 4. There's 4 subscripts. So it's a fourth order tensor. And in this case, it's just written as a covariant tensor. 4-order tensor. Okay, and what's G? It's the determinant of the metric tensor. In the previous slide, we saw the components of the metric tensor, which we just read off and wrote down. And so we find the determinant of that. In this particular case, there is only 2, because we've got r squared and sine squared theta. They're the only 2 coefficients of the differential elements. So this is a much simpler calculation. Although, if you do it by hand, it's a bit tedious, takes a lot of paper, sharp pencil, and a bottle of aspirin. I know, I've done it. Okay, now so for Hilbert's metric, if we make this calculation, we won't worry about how it's done, as I said, because it takes reams of paper, but we get the result that K is equal to 1 over R squared. So if we rearrange that for R, we get R is equal to 1 over K. What does that mean? Well, that means that the R is actually the inverse square root of the Gaussian curvature. Now we know what R is. How many relativists tell you that? None, because they don't know. But that's the reality. Now let's consider the terms G0 and G11. And they say that they have values between 0 to infinity, including 0. And when R equals 2gm over c squared, we can put that in there and we find that G0 equals 0 and G11 equals minus 1 over 0. That's division by 0. We learned in primary school, can you divide by 0? No, it's undefined. But they say, no, this is a singularity. And sometimes they say, with a very unscientific term, they'll say, the metric blows up. It does it. Blows up. That's real scientific. Okay, now let's look at when happens when R equals 0. We've got 1 minus 2gm over 0. Well, that's division by 0 again. And G11 equals minus 1 over 1 minus 2gm over 0. So we've got division by 0 twice. And they say that's another singularity. In his book, Hawking says, in his book, The Theory of Everything, etc., Hawking says, the work that Roger Penrose and I did between 1965 and 70 showed that, according to general relativity, there must be a singularity of infinite density within the black hole. They think by dividing by 0 you get infinity. How does that happen? So in the book Tensor Geometry by Dodson and Poston, they say once a body of mass m lies within its Schwarzschild radius, they're calling it a radius again. It's not a radius. We've already established what it is. It relates to Gaussian curvature. And so it's not a distance, let alone a radius, in Hilbert's metric. So it's got nothing to do with distance. So a singularity becomes physical, not a limiting fiction. Well, that's marvellous. Divide by naught and you haven't got a limiting fiction. Also, by special relativity, we can calculate density, where m over v, well, m is with the mass of the moving body, v the volume of the moving body, and we get, in terms of the rest mass and the rest volume, this expression. Well, that forbids infinite density. But we saw earlier that according to Einstein's theory, both the principle of equivalence and the laws of special relativity must manifest in his gravitational field. And then we're told that they've got infinite densities. Well, if that's supposed to hold in his gravitational field, and it forbids it, doesn't allow it. So the idea of an infinite density again is pretty silly. I'll just put this up quickly. You might wonder what the real R is. Well, this is what real R is in the metric. You calculate this, and you get this expression in the middle. And if you look at this, if you take values of R less than alpha, you get the square root of a negative number. Well, that's not allowed, because it's supposed to be the real radius. Radius goes from naught to whatever, but it's not the square root of a negative number. That's the real radius. It's straightforward differential geometry. That expression is never found in the literature either. We find that Ric equals 0 is quite meaningless because it leads to all of this nonsense that I've been talking about with divisions by 0 and violation of the fact that the radius can't have a negative value. They say that the gravitational field of a black hole has a escape velocity of c. And they rearrange that value that they put in there. C is equal to 2gm over r. Well, what do we recognise that as? That's Newton's escape velocity. So they've put in, they're arbitrarily assigned to their constant of integration, they've assigned it in such a way to put in Newton's value for a square for escape velocity. But escape velocity is a two-body object. One body escapes from another body. What does it mean? That's what it means. So how can you have a two-body relation, even though it only contains a one mass in it, but it's an implicit two-body relation? How can that appear in a solution for a alleged set of equations that pertains to a universe that can only contain one mass? You can't. So it can't be there. We see here that according to Hawking again, I had already discussed with Roger Penrose the idea of defining a black hole as a set of events from which it is possible to escape to a large distance. It means that the boundary of the black hole, the event horizon, is formed by rays of light that just fail to get away from the black hole. Instead, stays hovering on the edge of the black hole. So on the one hand, they say the escape velocity of the black hole is c. That means light can escape. On the other hand, they're telling us light can't even leave. What? So that's pretty silly. Here's another one, how they say that Newton's theory predicts it. In the paper, this paper here by Salotti, Miller and Sciama, they say, I'll read the top and bottom, the bit in the middle is just a quote from John Michell. In his famous article of 1784, which is seen as being the beginning of the story of black holes, John Michell wrote this, blah, blah, blah. There are at the very beginning, the theoretically predicted properties of Newtonian black holes were discovered together with a carefully worded statement about how it might be determined observationally whether such objects do in fact exist. But this is the so-called Michel-Laplace dark body. It doesn't possess the signatures of the alleged black hole, so it's not a black hole. Well, why? First, the black hole requires irresistible gravitational collapse. That doesn't. It has an infinitely dense point mass singularity. That doesn't. It has an event horizon. That doesn't. It exists in a universe and contains only one mass. That doesn't. It's got lots of them, right? And the principle of superposition applies, therefore, there. This sits in a universe which is described by a three-dimensional Euclidean space, whereas the other one is described by an object in a four-dimensional pseudo-Riemannian metric space. Well, they're not even in the same geometry. So we see that the Newtonian Michel-Laplace dark body does not possess the signatures of a black hole. So it's not a black hole. But they'll tell us as you see there, that it's a black hole. I'd like to quickly say something about Big Bang. It was mentioned by the previous speaker, and it was conjured up by the Abbé Georges Lemaitre, who was a Belgian mathematician and Catholic priest. Now you'll see here, Lemaitre was at the time both a member of the Catholic hierarchy and an accomplished scientist. Alfvén reported that Lemaitre said in private that his theory was a way to reconcile science with St. Thomas Aquinas' theological dictum of creatio ex nihilo, or creation out of nothing. And in January 1933, Lemaitre travelled with Einstein to California for a series of seminars. And after Lemaitre detailed his Big Bang, Einstein got up and applauded and said, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened." Well, what's the problem here? The problem here is that Lemaitre has admitted to Alfvén that he used his ideology to predetermine the outcome of a scientific inquiry. That means he's violated scientific method. Simple. Imagine an engineer using his ideology to decide on how he's going to design and build a bridge. Oh, I don't like the way we do it. I'm a communist, or a capitalist, or a minutist. I'm going to decide that I'm going to do it my way. So Lemaitre did that. Now, the other thing about it is, as I said, there are no solutions for more than one body. So the Big Bang creationism treats the universe, the whole universe, as completely filled by a single, indivisible mass of uniform density and pressure. What does that describe? One body, again. But the universe is full of billions of stars, billions of galaxies. So this is a totally meaningless model. You see the analogy often in textbooks where they're blowing up a balloon and they've got spots all over the balloon and they say these are all the galaxies. Where do they get them? This is a single body problem. So the analogy is quite false because it gives you the idea that you've got many masses. Well, this is not true because it's indivisible, because it's treated as a fluid of uniform pressure and density. So we got again back to the old problem that Einstein's theory can only describe an empty universe or a one-body universe. Gravitational waves. This is important. I've quoted Dirac here. If you see here, he says that you can't obtain an expression for energy of the gravitational field satisfying the conditions that when added together forms of energy, the total energy is conserved, and two, the energy within a finite three-dimensional region at a certain time is independent of the coordinate system. Now he goes on to say here, the best we can do is use the pseudo-tensor. This is a very important point. I'm going to come to that very soon. And then he says, let us consider the energy of these waves. Owing to the pseudo-tensor not being a tensor, we do not get in general a clear result independent of coordinate system. And there is a special case in which we do get a clear result, namely when the waves are all moving in the same direction. Well, this is Einstein's pseudo-tensor. We see that it's a second-order tensor and it's mixed, U and V. Okay, now, the first thing is that Einstein says that this describes the energy components of his gravitational field. Now, that's implicated with his gravitational waves. Here we have an expression. Einstein writes the total energy and momentum of his gravitational field as E is equal to the sum of what? The pseudo-tensor and the energy momentum tensor written in mixed form. Then he takes an ordinary divergence. He can't take a tensor divergence because he hasn't got a tensor sum. He's got a pseudo-tensor plus a tensor. So he's restricted to this kind of operation. And then he says, thus it results from our field equations of gravitation that the laws of conservation of energy and momentum are satisfied. And we have to introduce the totality of the energy components of matter and the gravitational field. That can't be true. This is a complicated looking expression. I've actually explained it to you. It's really simple when we do. You see that the energy, that the pseudo-tensor is defined by the top. Square root of minus g is just the square root of the components of the determinant of the metric tensor. And L and the other parts here are derivatives of components of the metric tensor. We look at L. L on the left, there's the components of the metric tensor again, but written in contravariant form because they're superscripts. And all these gamma functions, complicated looking stuff. Let's have a look at what a gamma function is defined as. It's, on the left you see the components of the metric tensor again, and then we see in the brackets the first derivatives of the components of the metric tensor. And so up top there, they've just used this shorthand for the derivatives. Okay? Now in tensors, written in mixed form like this, you can perform something called a contraction. And the contraction is, you set the top and the bottom suffixes equal. So we make UV and U equal. We get this expression. Okay, and we get what's called an invariant. T is equal to T to the power to the superscript U and subscript U. Now, if we perform the calculation, we get that bit there in brackets becomes 2L. And if we stick that back into the equations, we get this, and rearrange, we get this for the value of the pseudo-tensor. It's L over minus G. Okay. Now, bearing in mind the definitions of L and G, we see that the invariant, L over the square root of minus G, is composed solely of the components of the metric tensor and their first derivatives and nothing else. That's pretty straightforward. We know what first derivatives are from high school, and if we don't take the derivative of it, well, that's it. So, Einstein's expressions then, we see a result for his metric tensor is composed like this. But Tullio Levi-Civita and Giorgio Ricci Cabastro, the two Italian inventors of tensor calculus, proved in 1900 that such invariants like this don't exist. So in other words, Einstein's pseudotensor is a meaningless concoction of mathematical symbols. It looks pretty, but it means nothing. And so his energy and his conservation of energy are totally meaningless because the pseudotensor is rubbish. Now, this means that we have to rewrite Einstein's field equations in this form. I've written it there on the left-hand side, just rearranged it, and then I can write it in mixed form, doesn't make any difference, and we compare the mixed form with the expression for energy. And what do we see? That the energy momentum tensor is still there, but in place of the pseudotensor, which we know is rubbish, we've got now GUV over kappa. So now GUV over kappa, that's a tensor. So we've got a tensor expression for his field equations, and it's also an energy expression, right? But Pauli says that Einstein raised the objection to this formulation that with this definition of the gravitational energy, the total energy of a closed system would always be zero. And the maintenance of this value of the energy does not require the continued existence of the system of one form or another. The usual kind of conclusions could not then be drawn from the conservation laws. Well, in other words, Einstein's field equations now violate the usual conservation laws, well established by experiment. So his field equations are now in conflict with experiment, right? The total energy is naught, so how can you localize energy? You can't. There are no gravitational waves, you know? So the gravitational wave, again, is completely nonsense. Another thing I'd like to say about gravitational waves is they usually derive from the linearized form of Einstein's field equations. Why do they linearize them? Well, because they can't solve the nonlinear systems, so they linearize them. Any engineer knows that that's a big problem. If you start linearizing nonlinear systems, you start throwing out a lot of the important parts, right? Well, when you do that with Einstein's field equations, what you get is a set of equations that are not coordinate independent. But according to Einstein, all the laws of physics must be coordinate independent and therefore expressible in tensor form. Now, the fact of the matter is, with the formulation now of the linearized equations, the speed of propagation of gravitational waves according to Einstein is c. That's not true, because in the non-linearized system, they are coordinate dependent. So you can select any set of coordinates you like and you get any speed you like. So in other words, select a different set of coordinates, the propagation of the gravitational waves is greater or less than c. It's any one you like. So which one do you want to pick? Einstein and his followers arbitrarily pick the one that they want to satisfy the desire of the statement that they want the gravitational waves to travel at the speed of c. This is totally arbitrary, and so it has no physical meaning. All the other coordinates are just as valid. So again, the gravitational wave is completely meaningless. That's why LIGO has always been destined to detect nothing. And how much does it cost? I think it's well over $1 billion now. Other parts around the world, countries around the world, including Australia, have counterparts. They're looking for gravitational waves from binary black holes. You know, we know that that can't be possible. You know, so what are they looking for? They're looking for a phantasm. It's always been a phantasm. And why? Based on completely unrealistic or incorrect analysis of the field equations and Einstein's theory. Now, there's a couple of things I'd like to mention quickly here before I finish in relation to the electric universe, because what I've talked about so far is why Einstein's concept of the gravitational field cannot hold. And so it's a dead theory. It can't be saved, and his pseudo-tensor attempt to do that fails because it's a meaningless piece of mathematical mumbo-jumbo. Nikolai Kozyrev was a Russian astronomer, and he discovered the atmosphere of Mercury, and he also discovered lunar volcanism. But in his doctoral thesis on sources of stellar energy and the theory of the internal constitution of stars, I recommend that if you were interested in this, to take down this website, and you can download it for free. It's a very interesting paper. It was written in the 1940s, and what does he prove? He proves that the standard model proposed by Hans Bethe of the carbon-nitrogen thermonuclear fusion cycle for the Sun is complete nonsense. He shows that the temperature at the core of the Sun, and hence of other stars, is so low that it cannot initiate and sustain a thermonuclear reaction. He also shows that the Hertzsprung-Russell diagram for evolution of stars, etc., is completely erroneous. And he also shows that E equals mc squared does not account for the energy from stars. In other words, stars are not losing matter, not losing mass. They are stable. And he says, we came to the conclusion, which is very important and was partly mentioned in earlier talks, that the radiation from stars acts as a kind of regulator so that stars remain stable for billions and billions of years. Now, this is important because it shows that the electric universe ideas have support from an analysis done by Kozyrev back in the 1940s. It was only in 2005 that Kozyrev's paper was translated into English by the Russian Dr. Dmitry Rabunsky and myself, and published in journal Progress in Physics, because we thought that it was very important to be known. And Kozyrev offered no alternative as to how stars radiate and what their internal constitution is. He just says what it can't be. This is very important because it shows that the standard model doesn't hold, and it's been known since the 40s. What happened to that knowledge? It's been completely unknown outside the West. Finally, Professor Pierre-Marie Robertet of Ohio State University here in the United States has written a series of papers, and I've given you the website where you can find them. There are a number of papers there, and you just scroll down to the year 2011, and in volume 3 you will find all his papers there where he proposes a liquid plasma model of the Sun. Now, this has implications for the electric universe paradigm because of the plasma nature of the thing. Now, I asked Pierre, how did he come up with this idea of liquid plasma? He said, well, I coined the term because charged particles such as plasma have a order. And not only that, they flow like a fluid under the influence of electric and magnetic fields, right? So I think there's a great deal of information here that would be very useful to the electric universe ideas as well, because there's probably a lot of overlap here, and we can get good ideas from one another by studying these papers.